Well, let's work uh, an optimization practical application problem. And this is a classical problem of application for differential calculus. And it's about a carton box, right, like this one. This, I draw a little box here. And the problem is that the manufacturer of this box wants to maximize the volume, the volume inside the box. And this is an open box, so it doesn't have the the cover on it. Just is an open box. But the square surface of material equals 108 square inches. And this guy who is going to manufacture or build this box wants to maximize the volume using only this amount of material. So the question is, what dimensions of the base, in this case base is x, and the height is noted as y, are needed to get the maximum volume. Okay. If we disassemble this box, we can imagine that we come up with this piece of material to construct the box. And if we agree, this x is the length or dimension of the base, which is this x right here, and the height of the box is represented by this y over here. So the first thing that we need to do is to get the volume formula, and right now we are um, we have a two variable function here. This is volume for x and y, and if you agree, this is equal to x squared times y. Okay, so x squared times y, and that is the formula for the volume. Okay, let's now calculate the formula for this surface. So this is, let's say that this is surface, and let's say this is the area of this piece of carton. So carton board, let's write a little bit here. This is x. So the base of this box is equal to x squared. So this is x squared plus, and the area for this is 1, 2, 3, 4 times x. 1, 2, 3, 4 times x. 4 times x times y. Okay, because you have x times y, x times y, x times y, x times y. So the sum of these four plus x squared is the area of this squared surface. And we know that this area is equal to 108 uh, square inches. Okay, well, the next step, we need to isolate y of this out of this expression over here. So if we want to isolate y for this case, let's solve this for y. If we have this y here, then this is equal to 108 minus x squared. This is 108. If we move this x squared to the right, this will become negative. and divided by, if we move this, this is adding, we move this is going to be subtracting, and then this is a product. So if we move this 4 times x right here to isolate x, we will come up with this solution right here. So if we solve for y this expression, y is equal to 108 minus x squared divided by 4x. Okay, uh, replacing the y in the volume formula, we will come up with this. So our new volume is equal to x squared, this is this x squared over here, times y. And y, we know that y is equal to 108 minus x squared divided by 4x. Okay, and that is our new volume formula, because y is represented by this amount as a function of x. Okay, so if we start to solve this, this will be equal, let's say that this is equal to x squared times 108 minus x squared divided by 4x. Okay, and if we simplify this, we will come out, this is 108 x squared minus x to the fourth divided by 4x. Simplifying here, this x will cancel with this, so this is equal to 108 times x minus x cubed divided by 4. Okay, and dividing this number, this is equal to 27x minus x cubed over 4. So this is the volume of, this is the objective formula. This is the formula of the volume in terms of this area, and from this expression which represents the surface. Okay, once we have, um, this is the new volume formula, so we need to calculate the derivative of this function, because we want to find the maximum or the critical point of this function. So let's differentiate this expression. So if we want to calculate b prime of 27x, the derivative of 27 is just 27 minus derivative of this is 3 over 4, 3/4, and x squared, applying the power formula for this. If you say this is 3/4, it's going to be on the front, and n minus 1 here is x cubed minus 1 in the exponent, or this is 3/4 times x cubed. Okay, so this is the first derivative of the volume, and we want that derivative to be equal to 0. So if we do that, and then we can simplify this expression and making that equal to 0. This is equal to, let's see, that this is equal to 3/4 times x squared equals 27. Okay. Doing the math here, if we make this x squared is going to be equal to 27 over 3/4. Okay, doing the math here, we will end up with this x squared equals 27 times 4, that is equal to 108, and 3 times 1, this is equal to 3. So x squared equals 36. Okay, solving this, we will see that we have two solutions. So x is going to be equal to 6 and x is going to be equal to -6. In this case, we will choose the positive number because we cannot have a negative number in this type of problems. So this is the value for x. So if we want to maximize the volume of this box using this squared surface, x will be equal to 6. And now it's fairly easy to calculate again this expression using the last equation that we found. This is equal to 108 minus x squared, which is 108 minus 36, divided by 4 times x, which is 4 times 6. This is equal to 24. And if we do that, let me do the calculations here. This is equal to 72 divided by 24, and that is equal to 3. Okay, so x is equal to 6 and y is equal to 3. And with these two dimensions, the derivative of this function will be equal to 0, and that is the solution or the answer to this problem. And now we can tell this box manufacturer what the dimensions of base and height are needed to get out the maximum volume out of this box using 108 squared inches. Okay. Then there's another, uh, let's say, validation that we can use here. We can calculate the second derivative of this, and we will find that this number here is maximum value. But in this case, it is not necessary to do that additional calculation because we are dealing with real-world application problems. So this, with a little bit of algebra, you have the formula for the general formula for the volume. You have the formula for the area, so you can break down this surface into a polynomial expression and then solve for y. Now you need to translate the general formula of volume translated into your new objective function, which is this one, and then do the translation, solve for y, calculate the derivative, make the derivative equal 0, solve for x, and then solve for y, and you will have your problem solved. Okay, this is one of the classical examples for differential calculus. I hope and I expect that it is clear for you. Most of you have done this before in your high school. Some of you maybe not. Please let me know if this is clear enough. And if you have any questions or comments, I will be aware of them via classroom, text message, or email. Stay safe.